It's not focusing. There we go.
It's not focusing. So what we're seeing there, that's 50 Hertz AC. That's coming straight out of the 12 volt terminals on the power pack. So 12 volts from is the root mean square voltage, so we can see that that's going a little bit higher than 12. We're sitting on 5 volts per division, so each of those squares on that screen is worth 5 volts, so we can see it's actually going up pretty close to 15, but the root mean square is going to be closer to 12. And so our challenge is to take this voltage that's going up and down and up and down and up and down and turn it into something that just flows in one direction, like a DC current is what we're trying to create. And the first thing I thought we could try is a diode. What does a diode do again? Yeah, only one way. The electricity comes out the end of the silver band, right? So we're going to try and connect that up in series. We're going to hook up a diode into the circuit in series with this, so that the current can only flow in one direction. What is going to happen?
It's only going to flow in one direction.
And what's that going to look like on the screen?
It's going to flow in one direction, but only half the time.
Will it be
That
positive?
makes sense.
Can you elaborate on what you mean?
Well, if it's going up and down and up and down and up and down, one direction, then the other direction, one direction, then the other direction. It's going to go in one direction, and then it's going to stop because it can't go the other direction, and then it's going to start again in the other direction.
Sounds like DC. Ready for this? What's going on?
Positive.
What's going on? What did you notice? What's changed?
Brightness.
Decrease in brightness.
Brightness. Why has the brightness decreased? Like, how much time have we got a voltage for now compared to how much time we had a voltage for before?
Half the time?
Half the time. So what's happened to the amount of energy that we're delivering to the light bulb? Yeah, we're only delivering half the energy, right? We're only giving the positive current to the light bulb and all of the current that tries to flow the other way. That voltage is seen across the diode, but the diode says no flow, and so there's no flow. And so, yes, we've got DC in that the current's only flowing one way. Yes, if you connected your cell phone up to this, it would charge. It's pushing the current one way, but it's not going to do a very good job of charging your cell phone, because sometimes it's below the voltage that you want to charge your cell phone to, and sometimes it's higher than the voltage that you want to be charging to. And so, yes, it's DC, but it's not very good DC. So this is single diode rectification. If we just have one diode and fire the electricity through it, we get something that looks like that. What we want to do is have what? How do we want that to look?
Without the bits and the troughs and maybe equal bits.
We want to have the other bits in the middle.
Yeah.
Is that what you're saying?
Yeah.
So we want to turn the bits that were negative, we don't want to get rid of them, we want to make them positive.
Yeah.
Okay. Check this little puppy dog out. There's 4 different diodes all connected up together in a bridge. We call it a bridge rectifier. So when we connect 4 things in that kind of square shape that's twisted on its side, we call that a bridge. So 4 diodes like that, bridge rectifier. We've got a capacitor sitting there too. We're going to first of all just try it with the bridge rectifier and see what comes out if we put that as an input. What do we notice? What's happened?
Positive.
So somehow by connecting, we're going to talk about this in a moment and draw some pictures on the board and work it out. Somehow by connecting 4 diodes together in a bridge, we've managed to get all of the current to flow in one direction. Now, is that DC? What's that looking like? What's the problem with that? What's it doing? Is it a constant voltage? Is it going up and down?
Yeah,
Would we like it to be a constant voltage?
probably.
Should we make it a constant voltage?
Oh no, maybe.
Let's try that, shall we? So what we're going to do is just connect a capacitor across the terminals and just see what happens as we connect the capacitor up. What happened? Few changes. Are you seeing it?
I wish I couldn't.
So, what's changed on the screen?
So more confined.
It's more confined. It's got rid of the peaks and the troughs. And so, the bigger the capacitor, the more we can confine that voltage to one region. So what the capacitor is doing is charging up. And whenever the voltage goes above the capacitor voltage, it charges up a bit more. When the voltage drops below the capacitor voltage, charge flows off the capacitor into the light bulb, and the capacitor holds that voltage up a little bit higher for a little bit longer while the AC goes down to zero then back up. The capacitor smooths out that big drop down and then back up again. And what do we notice happened to the brightness of the light? Went brighter, right? So we're actually getting more power out of it by connecting that capacitor just up in parallel with our bridge rectifier.
So is the shape like that because as it goes down, suddenly the capacitor brings it back up?
Yeah.
Or, okay.
Yeah, so you should be seeing a kind of capacitor just charging, capacitor charging, capacitor discharging, capacitor charging. What do you notice about the size of that capacitor in there compared to the one that sits inside the power pack?
Very tiny.
Very tiny, and so as we make a bigger and bigger and bigger capacitor, that smoothing effect gets smoother and smoother and smoother until we have a really big capacitor. It makes it really smooth. So now we're good, I think, on how to turn something we plug into the wall into something that we'd be kind of happy to charge our cell phone on. So what do we do? What's the first thing that we do to change the 240 volts down to the 12 volts that we want? We have a transformer first. How do we change the AC from the transformer into current that just flows in one direction?
Diode.
With 4 diodes and a bridge rectifier. And then what do we do to smooth that voltage?
Capacitor.
Connect a capacitor up. And so that's how rectification works. And really, that's what's inside one of these. A power pack just has a transformer, then a bridge rectifier, and then a capacitor. You plug in stuff and it goes. Thing works. So remembering that these symbols here are diodes, and what they do is they just allow, on a very simple level, they just allow current to flow one direction. So the current can flow in the direction of the arrow, but it can't flow against the arrow. So what's complicated is that we put AC in to these two terminals here, and that means that the top one is positive sometimes, and the bottom one is positive sometimes. The top one's negative sometimes, and the bottom one is negative sometimes. And so we have to think our way through what's going to happen to each of these diodes to work out how this makes the current that we put in into DC. So thinking about this one first as positive, if this is positive, we've got current trying to flow along this way. Which one of those two diodes is it going to flow through? The right one or the left one? Right one. It's going to flow through the right one. So we're going to get that current flowing that way. And then there's going to be some resistor connected there, and the current can flow through that resistor, back along here, Now, we've got two diodes, and they're both ones that theoretically this current can flow through, but there's only one that it's going to flow through. Why is that? Which is it going to flow through, the top one or the bottom one?
Bottom.
It's going to flow through the bottom one. And it kind of makes sense just logically, otherwise we've got current going in a circle, but we can make even more sense of it because it's going to drop some voltage over the resistor here, which means that this voltage here is now lower than this one here. So in fact, it can't flow through that one because that's a higher voltage than here. So it's not going to flow in the direction of a higher voltage. It's going to flow down through that diode there, and then that voltage there is higher than this voltage here, and so it has to flow that way. And so when this one's positive, the current flows in, through, and through, and when the bottom one goes positive, what happens then? The current goes in, goes in, goes in. Which way can it go, left or right?
Left. Right.
Right, it goes through the right-hand one, and it can't go back against that diode, so it has to go through the resistor, and it flows back along here, up here, and this point down here is now a higher voltage than this point here, so which diode does it have to go through?
Top one.
Has to go through the top diode, and then once again that voltage there is higher than here, and so it has to flow back along there. And so what we've got is that when this is positive and this is negative, the current follows the blue arrows, and when this is positive and this is negative, the current follows the red arrows. And what we can see, what we really like, is that when it passes through that resistor, it's always going in the same direction. And when we connect up the capacitor, if we want to smooth it, we just connect up the capacitor like that. So that as this goes high, the capacitor charges up, and then as that current drops, as the voltage drops towards zero, the charge flows off the capacitor and through the resistor until this point goes to a higher voltage again. And by doing that, that capacitor smooths out that kind of bumpy DC that comes out of the bridge rectifier into nice smooth DC. Ideally DC should be like that, but what we got out was a bit of a wiggle still. A wiggle that's at a constant-ish value. It's confined between